Welcome back, quantitative analysis students. This is Mr. Marquetta, and I'm here to help you with integration today. We're going to learn about indefinite integrals, and we're also going to learn about the power rule and how to use U substitutions along with the power rule to get answers for integrals. Today is July 29th, 2021. First, let's talk about what is an integral. The word integral, or we could call it integration, that act or that idea, it's an operation just like plus and minus and divide and exponent. It's an operation. It's the inverse operation of taking the derivative. So if you have something and you take the derivative of it, it gives you something else. If you take that something else and take the integral of it, it will bring you back to the first thing you had. They go back and forth. The integral of the derivative is the original and vice versa. So when it comes to the derivative, there are some important things we have to talk about before, or rather the integral, before we start trying to do them. And I want to talk to you about the actual notation and the anatomy of an integral. If you take a look here, first I want to mention, if you've ever seen, I'm sure you've seen a violin before or a cello. If you look closely at the body work of that violin, you'll see there's an interestingly shaped hole there. That's called an F hole. And that's called an F hole because of music reasons that we don't have to go to. But that F hole also appears on the cello. And it is basically the same exact symbol as what you see for the integral. Now, you can draw the integral, it's supposed to kind of look like a capital S because it represents something of a sum. But for the most part, it's a beautiful, smooth, curved symbol that we use. And it is kind of like the beginning of something, but you have to include the end of something. And if you look at this, we have a couple of things to point out. I'd like to focus on them on each piece one at a time. Let's start by talking about this piece right here. The actual symbol itself, which is called an integral sign, and also this thing right here, which is called a differential. The integral itself, the symbol that you draw, that's that nice curve, it's really not just that. It's that, and it has to have dx at the end. They are the same thing. It's kind of like if you want to draw a parenthesis that starts up, an open parenthesis, I do expect to see a closed parenthesis somewhere. And it's the same idea with when you write an integral. We expect to see dx at the end, or dy, or dp, or d whatever particular variable you're taking the integral with respect to. It is crucial that you put it in there. If you don't, it's incorrect. It's like writing incorrect grammar in mathematics. You have to put the differential at the end so that the person who's trying to figure out the integral knows what variable is the variable to have respect to. Also, we have in here, and I'm going to change color to illustrate, we have in here f of x, and f of x can be any old function. It can be x squared plus 2x plus 1. It could be 1 over the square root of blah, blah, blah. It could be cosine and logarithm. But in other words, f of x is a funny algebraic expression that goes in there. So when you do an integral, you're going to have an integral sign. You're going to have an algebra thing. Okay, then you're going to write dx at the end. And the thing will be in terms of x. Also, we have some other important things here that we're not going to talk about until next time, but it is important to make mention of them. I'll use green for them. These are called limits. Here you have a to b. And for now, we're not going to think about how they work. We're going to leave them out. Having limits like that, when we're done with the integral, we do an extra step that has to do with substitution and subtraction. And it's really very basic arithmetic, especially if you have a calculator, but it's just one more step that you can add on to the act of doing an integral. That would turn it into something we call a definite integral, meaning your answer would be a number when you're done if you were looking at something that had limits like this. For chapters 12.1 and 12.2, we're going to do something we call indefinite integrals, which means your answer is not a number, and there are no numbers like this to substitute and subtract. Instead, your answer is an actual algebraic expression, and you won't be doing substitution, so you won't see numbers above and below the integral like that you see over there. So let's get rid of those green circles, and let's pretend that those parts are not there right now. There's also some vocabulary we could talk about. We like to call that symbol the integral sign. We like to call the function that we're integrating the integrand. When we do have numbers above and below, they're called the upper limit and lower limit. X is the variable of integration, or the variable with respect. They also call it the dummy variable. And the whole thing as a whole is called the integral. And the way you say it is the integral from a to b of f. Sure, all my friends are in here. I have someone waiting. Okay. Now, let's just jump in and think about that idea. So an integral is the opposite of the derivative. So you know how to find a derivative. How can I look at something and think, okay, I'm looking at the derivative. What was the question? It's kind of like Jeopardy, where we give you the answer and we ask you what is the question. Factoring is very much like that in mathematics as well. So what I'd like to do is focus first with you on example 1, which I have them in reverse here. They're backwards because they kind of go hand in hand and they're saying the same thing. But I want you to think first about the idea of the derivative of 3x squared. Something, I took the derivative of something and I got 3x squared. Let's look closer at that. Using your imagination, can you imagine what that must have been? What did you take the derivative of and it gave you 3x squared? If you think about it after you've done all your practice, you should think, well, x cubed would do it, wouldn't it? A little trial and error, and you'll understand what I mean. Let's start by changing this over. Let me stop this share. I'm trying to tell you that the derivative is 3x squared. At this point, everybody, please click view and make it speaker view. We're telling you that the derivative is 3x squared. So what was the function? If the function is x cubed, you might realize that taking the derivative of it would give you 3, bring the exponent down and make it a coefficient, and then lower it by 1, making it 2. In other words, one way I could do it is I could think, let's take this number right here and bump it up 1, add 1 to it, and then let's divide by whatever this number is right here. That is the very basic function of what it means to actually take an integral. You, instead of subtracting like you did when it was an exponent, when it was a derivative, you subtract 3 minus 1 gives you 2. For the integral, you take it and you add 1 to it, bringing it up to 3. In other words, you're trying to return back to what it was. Likewise, the multiplier outside, it would only be there if you brought it over. So to multiply, the opposite is to divide. Now, you could look at this and go cross-eyed and stare at it for a little while and think long and hard about it. But when it's all said and done, there is a basic concept. And the basic concept has to do with taking the actual exponent you see, bumping it up, and then dividing by that number. So make it the new exponent and divide it as well. In that regard, it would look like this, 3x squared. So instead, make it 3x to the third over 3, and see how they knock out? See how the 3 appears here and here? It makes everything work so perfectly that you get the x cubed. So what we want to do is develop a new approach so that every time we see any derivative, we can do something to it with math to get the original function back that we took the derivative of to get this. That's what finding the integral actually is. The way you would say that the derivative is this, find the function, is like this. Take the integral of 3x squared with respect to x. Now the answer will be x cubed. In the same way that if I say, here's x cubed, find the derivative. Okay, it would be 3x squared. It's kind of like the natural log and e to the power. They're inverses and they represent each other in reverse. Now, let's take a look at this one for a minute and think about this for a minute. X cubed, right? How about x cubed plus 27? What's the derivative of that? Well, the derivative of x cubed is 3x squared. The derivative of 27 is nothing, so the derivative is 3x squared again. How about if I was trying to take the derivative of x cubed plus 571 over 90? Okay, well, x cubed, the derivative we have established is 3x squared, and the derivative of this constant is nothing. In other words, the derivative of x cubed plus any constant at all should be 3x squared when you take the derivative of it. And that's why we have c as such a regular part of calculus. We do plus c because when you integrate, it's common to put plus c at the end to represent that. And by the way, the answer is, it could have been the derivative of y equals x cubed, or it could have been the derivative of y equals x cubed plus 27, or y equals x cubed plus any constant would have given me that derivative back, 3x squared. That's where c comes in. And what that boils down to is, don't forget plus c. Now, if you talk to math majors, there's a lot of funny jokes about don't forget plus c, because you could do a lot of very hard math and get integrals for very hard functions and get everything all perfect and forget to write plus c and you got the question wrong, and that's the joke. So plus c is like the negative sign that messes everything up if you don't pay close attention. All right, so the first thing we've established is we know there is a connection between this, and that the derivative of this is this, and therefore the integral of this is that. Now, in that regard, let's do another example where we're trying to figure out the integral of x cubed. Take a look at the way it's written here in your text. They're saying, for example, 2. If the derivative was x cubed, then what was f of x? All right, well, let's experiment. What would it be? Well, if I took the derivative of something and I got x cubed, it probably was x to the fourth because I know that's how I can get x cubed. Let's experiment. What's the derivative of x to the fourth? It's going to be 4x cubed, right? Okay. Well, the thing is, I was hoping to get the derivative of something that would wind up being x cubed. I got 4x cubed. How about if I make it 1/4 x to the fourth? Now what's the derivative of it? Well, 1/4 times 4 gives 1. And now x to the third. And look, now I got them to connect. What's the point? The point is I'm trying to prove that the way to figure out an integral is to take this exponent, add 1 to it, and then use 4 not as your multiplier, but as your divider. Here it is, 1/4. Some students will write it this way, x to the fourth over 4. And mathematically, they mean the same thing, which is why your integral formula has that basic shape that the integral of x to any n power dx will always be x to the n plus 1 all over n plus 1. And don't forget plus c, of course, because that's the new joke here, is plus c has to be added in every time. So this is what we call the power rule of integration. It's based on the premise that when you take the derivative, there's a power rule that goes with goes a negative 1 and with a multiplication feeling, whereas here it's plus 1 and it's a division feeling. Okay, so you have some great examples there. And now it's just a matter of really kind of practicing them and getting comfortable with them. So I'm going to ask you now to take a very close look at what I have here. This is another snapshot out of your textbook where we're showing you the model of what it means to take the integral of a basic power function. And as you can see there, what we want you to do is take the exponent n, bump it up by 1, add 1 to it, and make your answer x to the new power of whatever it is plus 1 divided by, again, n plus 1. And don't forget to put plus c because of the concept of finding a derivative of something. When you find the derivative of it, it could be plus 20, it could be plus 99, it could be plus 1/3, it could be plus any constant, and it would still be the same derivative, so you have to always include the c. All right. Now, if you look down here, there's a little bit more. They explain it a little bit more. You don't have to go that far. If you could follow that logic, that's great. But after our conversation, all the things that you see written there in complicated calculus is basically the concept I was explaining, where the derivative of the integral is the integral of the derivative. And when you take a derivative of a c, you're going to get nothing, and all those other things implying that you should put plus c after you integrate and all that. So here's your powers of x formula. Learn it, live it, okay? All you have to do is take the exponent, raise it up 1, make that your new exponent, and divide by it as well. Very much like finding the derivative, just everything is backwards. Instead of subtract and then multiply, it's add and then divide, okay? All right, so let's see now if we could do some more complicated examples of these, and let's see if we can apply some other rules to there. So here are some great integration formulas. You'll see that they follow almost exactly the derivative formulas. Starting with on the bottom, and I'm going to zone in right now on the bottom. You'll see on the left is the corresponding derivative rule that we have on the right. On the left, the derivative of x is 1. Therefore, on the right, the integral of 1 is x. And I want to mention, by the way, with my little arrow, I want to mention, notice for 1 that's right there, you don't have to put 1. You could just put integral dx. We know that 1 is there in the same way that it's like a constant coefficient of 1. You don't even have to write. Likewise, if we have a constant times something, you could pull the constant out of the integral and forget about it, work on the integral, and when you're done, multiply later on by the constant. Another feature of derivatives that is true that also applies to integrals. And last but not least, we have here something that connects with our sum and difference rule of integrals, of derivatives, meaning if you have a function that is the sum or difference of many small functions, you may go into each function separately, each little part, and take the derivative as each part and walk through the whole thing. You can also do that with integrals. So if you're integrating and you see a list of terms in a polynomial, you can act like you're answering 5 little questions, the derivative, or rather the integral of the first one, the integral of the next one. And if you want, you could write it with this beautiful fancy writing here. As you can see, You could rewrite it again and draw the integrals again and again, so on and so forth, like you see there, to show that you mean to integrate each piece. But notice, when you do that, it is important that every integral, every time you write an integral, don't forget, you haven't drawn the entire integral unless you've written dx. That has to go with it. And that's really crucial. If I'm going to write this integral, then I need to tell you where the end of the integral is by writing dx like that. And if you don't, then it's like you're writing grammatically incorrect. All right. Oops. I have some examples there to do. So let's go through those examples. I'm going to start with example 4. I'm going to go into example, well, I guess we should start with example 3, right? So here comes example. No, we should start with example 4. There's a reason I put example 4 first. It's a little more practical to start with that one. Let's start with that one. It's the integral of, let me write it down, the cube root of x dx. Okay, so we'd like you to find the integral here. Now, we do have a power rule. Remember my power rule, and I'll go and get it when I need it. Here it is, by the way. Okay, I'm not going to need it quite yet. But there's the power rule. First, let me see if I can rewrite my integral so that it follows this template of something to a power. You know that the cube root of x is the same thing as, we don't need to put it again, as the integral of x to the 1/3 power dx. And that's an old rule we learned about exponents and roots a long time ago, that if the index is 3, then I guess the power is 1/3. Now, I have to figure out, according to our formula, if n is 1/3, maybe I'll put a little note of that. Now I have to find n plus 1, because the formula calls for x to the n plus 1 over n plus 1. The easiest way to do it is to think about how 1 plus 1/3 is, of course, simply 1 1/3. And the mixed number version of that is simply 4/3. Oops, 4/3. There are other ways to do it. Some students think about how the number 1 is anything over itself. So 1 plus 1/3. That's easy because 1 is 3/3. 1 is also 10/10 and 8/8, you know. And if you do it that way, you can come up with your 4/3. But either way you do it, 4/3 is what you get, which means that the solution here is x to the 4/3 power over 4/3 plus c. Now, let's talk about this arrangement here, how you're dividing by the fraction 4/3. It's looked down upon to give an answer as a fraction in fractions. If you are actually dividing by 4/3, it's the same as multiplying by the reciprocal, so you really should write this to look like this. See how in this scenario, it was being divided by 4/3? So it's being multiplied by 3/4. It's the same idea as multiplying by the reciprocal, but what happens is you're able to give a new expression that doesn't have fractions in a fraction, at least it's just one fraction, right? Now, again, don't forget plus c goes there. So here you have a great initial case of what it's like to take an integral of a function that is a power function. This one is a power function in disguise because it's got a cube root. You should know that n equals 1/3 in that situation, so you can rewrite it to be x to the 1/3 power. Now, after we have it x to the 1/3, we'll add 1 to it, making it 4/3. And with 4/3, we have to put that here as the new exponent and here in the denominator. When it's in the denominator, we're going to have to flip it because we're dividing by a fraction. It's the same as multiplying by the reciprocal of that fraction. And this is the most appropriate answer for you to turn in as your final answer for the integral. In example 4b, we're asked to do 1 over x squared. Remember, whenever you write an integral, not to forget to put that dx. You got to put that, that's part of it. Now, again, does this follow my format of a power rule integral? Take a look. I need a simple integral x to the n. That's not what I have here. But because of my algebra background, I know I can rewrite this to look like this. That's the rule of exponents, negative exponents, and fractions. So that be the case, I have to think now about how n equals -2. If n equals -2, I have to find out what is n plus 1. -2 plus 1 is -1. So this has just become x to the -1 over -1 plus c. Now, can we make that look a little bit nicer? Well, first of all, something divided by -1 is ultimately just something negative. And x to the negative 1 means 1 over x to the 1. This is the answer that we would expect for a question like that. Now, I'm pretty sure you could probably put this into Desmos and it'll probably give you a correct answer. But again, you should know anyway that you can finagle this into that and like manipulate this a little bit and make it look a little bit more comfortable like that one. Right? That, my friends, is example 4b. And while we're in this conversation about moving around with negative and fractional exponents, let's see how it feels to put them both together at the same time. We have a question, example 3, which really, like I said, shouldn't have been talked about until we did example 4. But now that we did example 3, this question might not be that hard. It's the integral of x to the negative 1/2. Let me just make sure that's what it is. Yeah. X to the negative 1/2. So n equals negative 1/2. Now what is n plus 1? You guessed it, it's going to be positive 1/2, which means that my solution will be x to the 1/2 over 1/2 plus c. So if you're dividing by 1/2, that's the same as multiplying by 2. So the solution is really 2x to the 1/2 plus c. And if you want to change it around, 1/2 means square root, so it really looks like this. Now, this is the same question as this. Oh, I forgot the dx. And the reason why is because here we have a negative, that means x should be in the bottom. Also, we have 1/2, that means x should be in a root. So just know that it's a matter of changing roots and fractions into negative and fractional exponents, like you see here. And then after you're finished with that, getting an answer using your n and n plus 1. Don't forget plus c. And if you divide by a fraction, change it into multiplying by the reciprocal. And then you'll be home free with all the questions. That's how you do integration. It's just like derivatives with a little twist. All right, so we got some great cases here. Once again, I kept all those little ideas there. We're going to apply some of these rules a little bit more now that you see down there the constant and the coefficient and the sum. Let's see if we can do a couple of cases like that. So for example 5, we have a couple of great scenarios. Let's start with the integral of 4 dx. The way you should handle this one is anytime you see an integral and then a number like that, you can take the number out of the integral like this. See how I moved the 4 out? The 4 is out of it. And now I'm asking you, what is the integral of the derivative of x? The answer is x. It's like saying, what is x plus 5 minus 5? What is x, the common log of it to the 10th power? It's the same thing. What's the derivative of it? And then integrate it. You're going to get x back. And also, in general, we want to remember, always, the integral of dx is simply x, of course, plus c. All right, that's example 5a. Example 5b is another trivial case like that we could use. We're saying about the integral of 8x to the 5th. So we ask you to find the integral of this. We'll start by taking the coefficient multiplier 8 and pulling it out like so. And now we can ignore the 8 and focus on the integral using the power rule. This time n equals 5. N equals 5 is a very easy one. Whole numbers work nice and easy. So I guess n plus 1 is going to be 6. So what we're going to say now is the answer is 8 times, and now the integral turns out being x to the 6 over 6. And don't forget plus c. At this point, we will be requiring that you multiply some little fractions. 8 is 8 over 1. You can do something like this. And we do expect you give us something like this, 4x to the 6th over 3. And always put that plus c at the end like that, like in big writing. It's the same. It's not supposed to be joined together up here or anything like that. Just put plus c at the end and you'll get that right. Our last case in number 5 involves the sum rule. It's the integral of x cubed plus 4x. All right. So the way we'll handle this is we'll take the integral of each thing. Some students don't write it all out, and you don't have to if you don't want to, as long as you understand how it works. But the correct show your work approach here would be to write the integral of x cubed dx plus the integral of 4x dx. That's how you would show your work in calculus. Next, we can apply the power rule right now to this. It's simply x to the 4 over 4. There's not even any multiplication involved in it. And then we could do something here by pulling the 4 out. Notice I didn't write plus c yet. The reason why is because I can wait until the very, very end and put the plus c on. Even if it looks like I should put plus c for this and put plus c for that, you don't have to because it's already just a constant anyway, and two constants would add up to a constant anyway. So the general practice is when you're doing an indefinite integral like these, you do the algebra, and when you're finally done at the end, at the very last moment, you put plus c before you present your answer. All right, so I integrated this part. This is finished. I have to focus on integrating this part now, but notice I have x there. Don't let that bother you. It's x to the 1, right? And in the case that x is 1, that n is 1 rather, it would be x squared over 2 is what I'd get there. And don't forget it's times 4 over 1. So I'm going to end up with 2x squared there. So it looks like this, x to the 4th over 4 plus 2x squared plus c. This is what we're expecting for your answer this time. In this case, the 2 that was on the bottom vanished completely because we had the 4 there. Sometimes that happens. In fact, you'd be surprised how much of the multiplication of fractions stuff shows up a lot when you're doing integrals. They just keep coming back. Little reducing fractions ideas shows up all the time. And it's important to keep an eye on that stuff. All right, while we're at it, let's talk about example number 6. Example number 6 poses a problem with a hard solution. We're asking you to find the integral of the quantity x squared minus 4, all quantity squared. Now, looking at a question like this, your first reaction might be to think that you could just go in and integrate x squared and then integrate -4 and so on. But ultimately, you really just can't. You have, because of the squared. This squared right here has a very significant meaning, and it's important that we follow the rule of what that means. There's really no easy way around this except to take some scrap paper on the side and just figure out how to multiply it by itself, because that is what squared means, is to multiply it by itself. So we're multiplying it by itself now. Using FOIL, we have x squared times x squared is x to the 4th. Outer, we have -4 times x to the 4th. Oops, I'm sorry, times x to the squared. Inner, once again, we have -4x squared. And last, you have -16. These two come together nicely to get -8x squared, which means this is the same thing as the integral of x to the 4th minus 8x squared plus 6. So can we remember this case? In a situation where you have a binomial squared like you see here, you actually have to stop and come over here and do some 9th grade algebra and multiply it out. Get your new trinomial and now rewrite this integral to be the answer of it multiplied out. And now you can start applying the different rules we've learned, like the sum and difference rule, which tells you that you can take the integral of each of these things. Okay, so there they all are. Now we do each one at a time. This one is x to the 5th over 5. This one has a -8, so I'm going to just put the -8. And then x to the 2nd power is x cubed over 3. And last I have a 6, so that's going to be 6x. And don't forget plus c. If you forget plus c, you're going to make a little mistake there. Don't forget it. All right? This is a case of the sum rule, along with the constant rule plays a role here, the coefficient rule plays a role here, and the sum rule that you do it to each one, and of course the power rule is all over that as well. All right, they have some great examples that you could follow, and they all follow those rules that I was showing you earlier. These are the basics of what it means to solve integrals or figure out the answers to integrals. It's the power rule. And in the same way that we have studied the chain rule, where if you find a function where you're taking the derivative and it emulates a power rule, then you can do it as long as you multiply by the derivative of what's inside. That plays a role also in the world of integration, and we call that U substitution. And we're going to do U substitutions next. Well, before we do that, let's take a close look at this application problem. It's going to involve that we do an integral, and then when we're done that we plug in the value. The question reads, sales records at Jaris Technologies show that the rate of change of the revenue, in other words, the marginal revenue, in dollars per unit for a motherboard is this much money, where X represents the quantity sold. Find the total revenue function of the product, and then find the total revenue from the sale of 1,000 motherboards. So this marginal revenue function, 300 minus 0.2x, that's something that I had to take the derivative to get that. So in other words, there is another function, the revenue function, that when I took the derivative of it, it gave me that MR, that marginal revenue. To find out what the original revenue function was, I have to do the inverse of derivative, which is integrate. So I'm going to integrate that. And when I'm done, I'll assume that is the total revenue function. And I can take that function and plug 1,000 in to figure out the answer to the question this time. Okay, so let's jot down the function first, the marginal revenue function, and then recognize that we need to take the integral of it. The function is marginal revenue is 300 minus 0.2x. Okay, so what we're trying to say is if this is the marginal revenue here, then I want the revenue. The revenue is going to be the integral of the marginal revenue. So that's going to be the integral of 300 minus 0.2x dx. That is the revenue function right there. Now, according to our sum rule, I can take the integral of 300 dx, and I could take the integral of minus 0.2x dx, like so. For both of these, I have a coefficient multiplier I can drag out, right? And this one is minus 0.2, integral of x dx. You may recall before we figured out the integral of x dx. I have it here somewhere, and I don't like doing the same thing more than once. Let's focus for a minute, friends, right here. Right? The integral of x dx is x squared over 2. We wind up crossing it out because of something else, but it's x squared over 2. So for this part right here, I'll write x squared over 2. For this part right here, I know the integral of dx is just x. And then these knock out nicely, don't they? So what's your final solution? 300x minus x squared over 10 plus c. And by the way, that 1 was over there. All right, this is what you're looking for. Now, the next thing you want to do is find for 1,000 motherboards. So to find it for 1,000 motherboards, we will plug 1,000 in right here and right here, get our solution, and it would be a number. Notice it would still be plus c. We'll leave that for a further explanation later on, and there's some explanation in your textbook about it, but when you do it in Web Design, there'll be a learning lesson about how to deal with that c. For now, when they say, what about when x equals 1,000, put 1,000 here, put 1,000 there, and figure it all out up until you get to c, and then write your answer with c. All right. Now let's carry on and talk now about what it's like to do U substitutions with these. And it's basically the same idea as the chain rule, but in reverse. First, in order to learn about how to do something like that, we have to talk about something we like to call differentials. A differential is going to be just the part of the integral that says dx or dy. Differentials are very subtle. It's just d and the letter. If y equals f of x is differentiable, and dy dx equals f prime of x, then you could say that dy equals f prime dx. So in this case, it's kind of the same idea as saying dy dx, but then multiplying both sides by dx. Ultimately, if you have a function like you see here for a and b, you basically just take the derivative of both sides, but don't forget to put the d at the end, and I'll show you just what I mean. Let's start with example 1. Notice the directions in examples 1 say find dy, not find the derivative. It says find dy, and that means you're looking for a differential which has a certain specific look to it. All right. So we're saying find dy if y equals x cubed minus 4x squared plus 5. There we go. This is example 1 out of chapter 12.2. Okay, so you want dy? We could do dy. In order to do dy, the left side is y, so the derivative of the left is dy. The right side is in terms of x, so the derivative will have dx at the end. What is the derivative? 3x squared minus 8x, is it not? And we've learned that already. We know that because of the power rule. The 3 comes down to become a coefficient. We lower the exponent 3 down to 2. Likewise, we take 2 and multiply it by -4. We get -8, and then we lower x squared down by 1. It becomes x. Last but not least, the derivative of 5 is nothing. This is the derivative. But don't forget when you're done to write dx. Why? Why are you doing that? Because we asked you to find dy, not to find just the derivative dy dx. We wanted dy. dy is this dx. If you divide both sides by dx, it'll read dy dx equals this, and that makes sense. So can we remember when they say find dy, it means take the derivative, but just don't forget to make it that the dx that would be down here, like dy dx, it's actually moved to over here in the case of a differential. All right, that's example 1a. Let's do one more case of that. Let's do it with different letters. This is example 1b. And in example 1b, they give you a function looking like this. U equals 5x to the 4th plus 11. Find du. Okay, to find du, on the left, that's easy. We take the d of the left, which is du. Now we take the d of the right, which is 20x to the 3rd. And then the derivative of 11 is nothing, but don't forget your dx. This is the solution we're expecting when you ask for a differential. So let's talk about the power rule and u substitutions now. Now you already know the power rule. There it is. If you're looking at an integral, what you do is you take the exponent and add 1, and that becomes your new exponent and also your new denominator. In example 2, we're asking you to find an integral, but the integral is of something other than just a number to a power. Let's see how we would work on doing that. This is the case I was explaining earlier where you're going to think of something we like to call a u substitution. This is example 2, and the integral reads integral of 3x squared plus 4 quantity to the 5th power times 6x dx. Okay. Now, notice that we do happen to kind of have the derivative of this right here. And these integrals are set up to have that very situation, such that you can actually find, if you look closely enough, you can find the derivative of this right here. And the way that you deal with rewriting this is not by multiplying it out. Let me start by saying you can multiply it out. If you want to do 3x squared plus 4 times itself 5 times and go through all that work, you could do that and you could integrate it that way. But that's going to be a lot of work, and it's harder to do it that way than it is to do what's a u substitution. In other words, we see something to a power. Let's say that u is that something like this. It follows now, since we've studied differentials, that du equals the derivative of this 6x dx. Look familiar? It's right here. And this is right here. So that means we can write this to be the integral of u to the 5th du. Now look at how simple this question is. This is a very simple question. But it's a matter of taking all of this and relating it appropriately with differentials, being clever about selecting which of these pieces will be u. Some students might accidentally think this should be u. A student might think 3x squared should be u. It's this whole piece that would be u in order to make it work. A lot of calculus is experimenting in this way until you find one avenue for what u will be to make it work. So that be the case, in terms of u du, this is going to be simply u to the 6 over 6. But remember, u is something that you made up. And now you're going to start to see all of the u jokes in calculus. There's a lot of funny jokes about plus c. There's a lot of funny jokes about u. Here's another great example. For example, u is not a variable that they want to hear about. U is something you made up. What is u? U is all this stuff. So this should read 3x squared plus 4 quantity to the 6th power all over 6, like that. In other words, I substituted in the u I just made up back into the position of u so that I have an answer in terms of x. And there's one last little thing here. Do you remember what it is? Yep, plus c. Don't forget plus c at the end of every indefinite integral. Why is it indefinite? Because there are no upper and lower limits. There would be little numbers floating and there aren't any. So I better put plus c. All right, example 2 is a great example of how to use u substitution. It's a great way to get your feet wet and get started. Usually they'll be kind about it and put the derivative right here so it's very clear and in plain sight. And you should be able to say, the derivative of this is right here. And the big trick to this is, remember, the derivative of any constant is going to be 0. And that kind of makes everything work nicely. And you'll see them using creative constants there. Let's do a couple more of these u substitutions, starting with example. We got a whole bunch of them to do. So let's see if we can work through these, starting with example 3. It's about the integral of 2x plus 3 under a root times 2 dx. So it's something of a puzzle. Can you imagine what you should make u such that when you take the derivative, it pops out quick and easy? You might notice the derivative of this is right here, isn't it? So first, I'm going to rewrite this without calculus. I'm going to rewrite this using algebra principles and make this 1/2. Why did I do that? Because I want to make sure, let me make sure that's clear, that's a 2. Because I want to make sure that I can take the integral, and it's easy to take integrals of things with powers, not roots. So I have to rewrite it first. Next, I'll say u equals what's in the parentheses there. So it follows now that du equals the derivative of this, which is 2x, the derivative is 2. 3, the derivative is nothing, so it's 2 dx. Again, this is differentials here. And notice here is all of 2 dx is going to be du. So I'm going to replace all of this with du. I'm going to replace all of this with u. So now I have the integral of u to the 1/2 du. Now, I think we did u to the 1/2 somewhere. Did we not? Hold on, I know I got it. I got it here somewhere, don't I? Didn't we do u to the 1/2 somewhere? I think we did. Hold on just a minute, guys. Hold on. U to the 1/2. X to the 1/2. Well, I thought we did, and I guess we didn't. That's okay. You know, I'm kind of surprised. I really thought we did that. That's okay. If we didn't do it, we'll just do it again. Let's do it again. So if it's u to the 1/2, recall that n is going to be a half, right? So if n is 1/2, oh, you know what, guys? We didn't do it, right? N equals 1/2. So n plus 1 is going to be 3/2. Why is it going to be 3/2? Well, you could do it a couple ways. You could say 1 and 1/2. That is 3/2. Or you could say 1 equals 2/2. And 1/2 together, that makes 3/2. Any way you look at it, 3/2 is what you get, which is why the integral here is going to be u to the 3/2 over 3/2. Now that's not very nice. We can change this to flip this, right? To over 3 with u to the 3 halves. What is u? U is this expression right here, 2x plus 3. So one last motion would be to write 2 times that correct quantity, 2x plus 3 to the power 3 halves, all over 3, and then you got it, plus c. Don't forget that plus c. This is the answer we're looking for the integral now. All right. For example, 4, we're asked you to find the integral of x cubed times 5x to the 4th plus 11, quantity to the 9th power. Okay, now, for the first time, we're going to run into some trouble here. We're going to have some issues, and we're going to get some ugly fractions to compensate. But remember, we do have one thing having the derivative of another. In this case, you'll notice that the thing you're raising to a power 2 has got a 4th power. It's to the power of 9, but the whole thing has a 4th power. One beneath that is the 3. So what we're going to do is we're going to work on getting the differential, but then we're going to try to solve it for x cubed. Start by thinking u equals 5x to the 4th plus 11. It follows now that du must be 20x cubed dx. So what I can do here is I see x cubed. I can rewrite this by kind of bringing this over here and kind of sticking it right in there to be the integral of 5x to the 4th plus 11 to the 9th times x cubed dx. Why would I do that? Why would I switch them around? Well, because now I could do this here so I can get and see how this is the same as this now. So what happened? Let's review. We started by realizing that we had to let u be what's in the parentheses. And after we figured out what u was in the parentheses, we did the derivative, and when we found du, we found the differential, we had something that kind of looked like what was left in the integral, but a 20 appeared, and 20 is not anywhere in the integral, so how do I deal with it? Well, first of all, don't flip out about 20. 20 is an ugly number. Welcome to calculus. Secondly, how can I figure out what I should put in? Notice this x cubed is over here, and this dx is over there. Might be practical if I switch them, and you can do that. That's called the commutative property. 5 times 8 is 8 times 5. Switch those two things around, and suddenly you have this expression on the right, x cubed dx. I can take this equation and manipulate it to be isolating x cubed dx, and it gives me this expression. So what I'm going to write now is it's the integral simply of u to the 9 times 1 over 20 du. Now, if you look at it now, it really doesn't look that hard after all. In fact, it makes it very neat and simple. To get the answer, it'll be u to the 10 over 10 times 1 over 20. And then what is u? U is this quantity, 5x to the 4 plus 11. So I'll write 5x to the 4 plus 11 all over, all to the 9. Oh, what is the 10? Sorry, all to the 10. But then all over, what is 10 times 20? 200. And don't forget plus c. This is what they expect here. All right, let's review. That one was pretty nasty. We see something to a power. We recognize u should equal that. So we write out u equals that. Then we do du. When we do du, we don't see the derivative here up here. Its only difference is that the x cubed can be moved over, but there's still a 20 lingering. So make your effort to try to solve so you can isolate x cubed dx. And I did that by dividing by 20. And now I have an expression for x cubed dx. We substitute 1 over 20 du into the position of that, like so. And we substitute 5x plus 4, 5x fourth plus 11 as u. So instead of this to the 9, it's u to the 9. And now you have a very basic integral. I forgot that. Yeah, a very basic integral. And you have to substitute a little bit more by taking the u and putting back the x expression. And as much simplification as you can. For example, you could do 10 times 20. Note, some students might make the mistake of thinking they slash out because 10 and 20 are in the same times tables. Know your times table facts and how to multiply fractions. In this case, you don't cancel. You multiply 10 times 20 to get your solution. All right, so it looks like we've conquered examples 3 and 4. Let's see if we could conquer example number 5 now. In example 5, we have the integral of 5x to the 4 times the root of x cubed minus 4 dx. Notice the root is always the first thing we have to handle and deal with. The root really should be a half power. So let's make this equals the integral of 5x to the 4th times x cubed minus 4 to the 1/2 power. And it's customary to make that power your u. So u is going to be what you're taking to a power, x cubed minus 4. That implies du is 3x squared dx. Now, here's where we have a little bit of a headache. Notice that we have, hold on just a minute. Oh, this should be squared. Yeah, it should. I wrote it down wrong, you guys. I'm sorry. I'm not trying to make it harder than it is. It's squared there. Okay, good to know. It is squared there. So notice that we have 3 here and 5 there. That's going to make things a little bit ugly. Don't let it bother you. We're going to try to make it that we can figure out 5x squared dx because this really should be rewritten to look like this. Right? And if I can figure out what 5x squared dx is, I'm home free. Right now I have 3x squared dx, so let's do it in steps. Let's get rid of the 3. I have du over 3 equals x squared dx. And then if I want it to be 5x squared dx, well, I guess I better do it by 5 both sides, right? Which implies now that 5/3 du equals x squared dx. Equals 5x squared dx. That means this whole quantity is the same as this. All right. Now, I'm going to take this and replace it with u. I'm going to take this and replace it with 5/3 du. And it's going to look kind of like this. It's the integral of u to the 1/2 times 5/3 du. See how I come up with that? And at first, when you look at it, it's kind of ugly, but remember, this is just a coefficient. It can be dragged out to the front. So let's do that. And now we got to figure out what is the integral of u to the 1/2. And once again, I did figure that out, didn't I? Somewhere. Here it is. Why do it again? Look at the mess it becomes. The integral of u to the 1/2 we have established is this 2/3 u to the 3/2. All right. Now there's a 5 here and a 3 here. Let's multiply everybody together. And we're going to get 10 u to the 3/2 over 9. Now what is u? We've already established that u is this expression x cubed minus 4. So this is just turned into 10 times x cubed minus 4 all over 9 to the 3/2 plus c. All right. Let's review. So you'll notice that we do have a higher exponent cubed than we do outside here squared. We're going to have to join these two together to make the differential. We say u is this, therefore, consequently, du is this, and you can solve it for 5x squared dx if you're careful by dividing by 3 and then multiplying by 5. You get this funny expression 5x squared. So 5x squared dx is the same as 5/3 du. So I can just replace that with that. giving me a new integral that looks like this. Then we integrate. Well, then we apply the coefficient rule 5/3 should be brought to the front like it is there. And now I have u to the half. And now I'll integrate u to the 1/2. I add 1, I get 3/2, and then I divide by 3/2, which means times by 3/2. And as you can see, we have a new multiplication of fractions case here. In this case, nothing knocks out. We just think 5 times 2 makes 10, 3 times 2 makes 9. And here's your new answer. But remember, it's in u. So you have to change it back. U was the variable for x cubed minus 4. So we put that in, and don't forget plus c. All right. We've got a couple more cases, and then we're going to be done for the day. And I do appreciate your close attention to the lesson, my friends. I know it's lengthy, but don't worry, we're on our way out. We're almost done here. Next, we're going to do example 7. And in example 7, you're going to see all kinds of funny, weird tricks going on here. This is kind of mathlete or math bowl or academia bowl or whatever you want to call it. These are the hard ones. So it's a matter of getting clever and looking at them and trying to come up with like puzzle solving techniques to get your solution. At a first glance, looking at this question, what would you do to try to solve this integral? How could you handle it? Well, remember Marquetta telling you that there has something to do with the higher power squared in the exponent, and 1 less than squared is 1, and you have x to the 1 here. So we should go in starting with u must equal this quantity. We should go in starting thinking that way. Now, if that be the case, we can believe that du is going to be 4x minus 4. But I'm hoping to get x minus 1 dx somehow, because that is dx. So to get that, I could do factoring, and see, this is where the clever puzzle solving stuff shows up. If you could realize this looking at what you just wrote, it might come clear to you that you're supposed to go like this and make it 1/4 du equals x minus 1 dx, which means this right here is 1/4 du, and this right here is u. See, they always boil down to a simple integral. The integral is really very easy. It's just the integral of u squared times 1/4 du, which is trivial compared to the other ones. And you figure that out, finish up, go back and substitute in the x expression for u, and don't forget to put plus c. But for example 7, the trick is starting with letting u be the thing inside the parentheses, find the differential of it, and see if you can manipulate this equation. This is the hardest part, manipulating this equation to fit what's left in the integral so that it all fits nice and neatly like a jigsaw puzzle. So let's finish up here. This will be, of course, u cubed over 3. And likewise, times 1/4 ought to make it u cubed over 12. And you know that we told you already that u has a value of 2x squared minus 4x. So we're going to make this 2x squared minus 4x quantity cubed all over 12. And of course, don't forget plus c. And there's your solution. In example 7, we have another case like that where there's a trick. Let's take a look at that one. Example 7b reads, we're taking the integral of x squared minus 1 all over x cubed minus 3x quantity cubed. Okay. Monstrous, really, but welcome to calculus. So let's start with, I don't like that denominator, so I'm going to rewrite this right now to have a negative exponent. I'll write it like this. I'll write x cubed minus 3x quantity cubed times, that's quantity negative cubed now, right? Because I brought it up out of the denominator. It's negative cubed. And now times the quantity x squared minus 1 dx. So I'm going to let u equal x cubed minus 3x. It follows now that du is 3x squared minus 3 dx. If only I had this, but if you look closely enough, just like in the last case, you could factor out 3 and get that. And then to solve and finish up, you should divide both sides by 3 to get 1/3 du equals x squared minus 1 dx. That means this can be replaced with du, 1/3, and this can be replaced with u. So simplify and substitute. Your new integral looks like this. The integral of u to the -3 times 1/3 du. After all this hard work, it's this that we have to figure out, and this is a cinch. So what we'll do is we'll start by taking the 1/3 out like this, or you could forget it and just put it in later. Either way you like to do it, that's fine with me, as long as you get the right answer. Now, u to the -2, if n is negative, I'm sorry, u to the -3, if n is -3, then n plus 1 is going to be -2. Watch out for that. Negative exponents are very easy to mess up with adding and subtracting. So I'm going to write 1/3 the way it is, and I'm going to multiply it by u to the -2 over -2. That's the new value. And that means that I have on the bottom 3 times -2, which is -6. And on the top, I have u to the -2. So don't forget, from the beginning of our question, we defined u to be x cubed minus 3x. So this ought to read x cubed minus 3x all to the -2 all over -6, and that'll be plus c, of course. If you want to get a little technical about it, it might be a little nicer for you to write it this way. That negative means that the whole fraction should be negative, like so. There is a 6 on the bottom, but there's also all this stuff on the bottom with a positive exponent and a 1 on top. So you might see when you're doing your web assignment practice that they require that you give your answers with positive exponents. And if you have answers that come out with negative exponents, then you have to take the negative exponent you see there, make it positive, but put it in your denominator in order to be able to get it. All right. So this is a great example of how to use a u substitution. Okay, now I've got one more example, and I'm going to pause, and I'm going to allow you to give this example a try. After you've seen so many great examples done here, I want to see if you could figure out, for example 8, we're asking you to find the marginal revenue for a product. Well, we're giving you the marginal revenue for a product, and we're asking you to figure out what the actual revenue was. So ultimately, what that really means, my friends, is to integrate the whole thing with respect to x. Remember, when you have over a root, it's the same as to the power of -1/2. I'm going to ask everybody to give it a try. Right now, it's 5:45, and in 15 minutes, I'll come back and I'll show you the answers to it. So let's take a little break here. We'll resume class at 6 o'clock, and I'm going to ask you between now and then to focus on finishing example 8. We'll reveal the answers to example 8 at 6 o'clock, and then we'll open the floor for questions and conclude and dismiss. Thanks for your attention. In 15 minutes, we'll come back and look at example 8. All right, friends, let's finish up. Now it is 6 o'clock, and as promised, I'd like to go through how you were supposed to do example 8 now. And then when we're done with that, I'm pretty sure that that's all we have. Do we have another one? Let me just look real quick. Do we? No, we don't. So this is our last one. After we go through this example, I'll open up the floor to any questions you might have, and then we'll dismiss for the day. All right, so we're going to talk now about this marginal revenue function. Let me write it down. We'd like you to find the revenue function. Here's the marginal revenue function. All right, well, here's the way it goes. If you want the revenue function, you need to take the integral of the marginal revenue function with respect to x. The marginal revenue function is all that dx. Okay, so now let's talk about this down here. When you have a denominator with a root, the exponent associated with that, and I'll make a little think bubble for you. Whenever you see something like this, it will be n to the negative 1/2. I need you to remember that. Anytime you have a root and denominator at the same time, negative 1/2 is what you get. If it was a cube root, it would be negative 1/3, etc., etc. So that being said, we're going to rewrite this first to be the integral of 600 times 3x plus 1 to a very special power, negative 1/2. Okay, and don't forget that that is plus 2. And the whole thing is dx. All right. So when you need to put parentheses around parentheses in calculus, it's a little more appropriate to use square brackets. They're kind of like capital parentheses. Now, I can take this integral and use the sum rule to take the integral of the first part and the second part like so. It'll be the integral of 600 times the quantity 3x plus 1 to the negative 1/2 power dx. That's our first one. And now the last one will be plus the integral of 2 dx. Okay, so what I did was I split up that radicand symbol and I put it there for each of the two things. Next, I'm going to apply the coefficient rule. The coefficient rule says that if you have a number in the beginning, you can drag it out of the integral like this. I'll take the 600 out. Well, I'll tell you what, before I take the 600 out, let's leave that for a minute. Before I take the 600 out, I'm going to focus on this one, but I'm going to try to think about a u substitution. I'll come back over later and deal with this. So just to take care of this one real quick at the end, it should be 2 integral of dx, which becomes 2x. Okay, and we'll come back and get that later. But to get this whole thing, I'm going to use a u substitution, starting with u equals 3x plus 1. It follows then that du equals 3 dx. That's because the derivative of 3x is 3 and the derivative of 1 is nothing. So du equals 3 dx. If I'm trying to do 600 dx and I need 3 dx, I can try to figure that out. Let's take a look at it this way. Integrate you put it in the other order, looks like this, 3x plus 1, quantity of the negative 1/2, but then write the 600 later, 600 dx. In other words, I've moved it so that the 600 is at the end with the dx. And the reason I did that was because I have a statement here that says du equals 3 dx. So what about 600 dx? I could get 600 dx if I'm clever and I multiply by 200 on both sides, telling me 200 du is the same as 600 dx. Kind of funny looking, but that's what I needed because I need to replace this with 200 du, and then I can replace this with u, which gives me a new integral, the integral of u to the negative 1/2 times 200 du. All right. So we've already talked about this, what happens when you do the derivative of something to the negative 1/2. I do have that somewhere, but still we're going to do it on the side. The integral of u to the negative 1/2 du is going to be u to the 1/2 over 1/2, which is going to be 2u to the 1/2. So this is 2u to the 1/2. And the 200 is there too, so it's times 200 because you can put that in front, right? Last, we have it's 400, and it's not u, it's actually 3x plus 1 plus c. So this is the question. This is what we're looking for here for your final revenue function. And we're hoping when you go through doing your work, you come up with a solution like this, carefully plugging everything in. Oh, there is one thing that we forgot. Don't forget, it's got the plus 2x that we did there too. So the actual answer is that plus 2x. Let's just rewrite it one more time. It would be 400 times 3x plus 1. And since it's to the 1/2, I could write it as a root like that. And then don't forget your plus 2x and then plus c. All right. So these are great examples to try to get comfortable with how you're supposed to use substitutions to figure out integrals. Today in class, we started with the basic premise of what an integral is, with the initial idea of how the power rule works and everything and how it's related to derivatives. And we went pretty far with it. We went even as far as using substitutions and using alternative differentials to be able to simplify and get our answers. There's a lot of playing around with negative fractions, negative exponents, fractional exponents, roots. It's all old algebra stuff. But if you get stuck with that, remember there's material in your textbook, and I'm here to help you with that too. I'm going to ask that everybody focus now on the next web assignment project, which will be due on the day of your next exam. Your last exam is going to be a week from today on Thursday next week. All right, we are going to stop our lesson. I'm going to close here, and then we'll open up the floor to any questions anyone might have. Once again, thank you so much for your close attention to the lesson, and I hope you guys have a great day and good luck with the material.